Hello, hello, all my beautiful calculus students. Today we're going to talk about some inverse trig functions, starting with y equals arc sine of x. As a little review, I just want to talk about the fact that y equals the sine of x is a function, which means for every element in the domain, there's exactly one element in the range. So for the sine function, your domain elements over here all consist of angles. We have angle measurements. So like for instance, pi over 6. The sine of pi over 6 turns out to be 1/2. Now you may be able to do that right in your head because you memorized it. Or pi over 6 would be the same as 30 degrees. Sine of 30 degrees is 1/2. Okay, so basically the sine function takes an angle measurement and sends it over here, and what you end up getting is some kind of a ratio. And in particular, if you're in an acute triangle, it would be your opposite leg over your hypotenuse. Okay, I think we all know what the sine graph looks like. Starting between 0 and ending at 2 pi, we have one complete cycle. The sine graph starts at 0, ends at 0, halfway in the middle it's also at 0, and halfway between its first two zeros it hits a high of 1, halfway between its last two zeros it hits a low of -1, and the cycle repeats. It keeps going and going and going every 2 pi. So therefore the period of the cycle is 2 pi. My question is, am I going to have an inverse function that goes backwards that can possibly take something that is a ratio and give you an angle measurement? And the answer is yes. F inverse is going to exist, but we have to do something called restricting the domain. Because if I want an inverse function, then I want the inverse to literally be a function, which means that every element in the inverse's domain, and this would be the domain of F inverse because we're starting here, and over here is where we end. So over here, what used to be the domain of the original function is now the range of the inverse function. So now we're going to start with ratios and end with angles. So in order for that to happen, I have to be sending each element in the domain of F inverse to exactly one element in the range of F inverse, which means I'm going to have to restrict the domain of my original y equals sine x function over here. So I hope you guys recall the whole concept of being one-to-one. So the sine function is definitely a function because for any x value, and I draw a vertical line that represents an x value. For any x value, the graph is crossing that particular x value just once, which means for every x value, there's exactly one y value that corresponds to it, thus making y equals sine of x a really nice function. Question is, would it be a function if you went backwards? Would every y value have exactly one x if I drew my lines horizontally? And that answer is obviously not. I can see that horizontal lines are going to cross the function repeatedly. As a matter of fact, because this function is cyclic, which means it keeps going and going back and forth, up and down in both directions, then every horizontal line is going to cross y equals sine x an infinite amount of times, as long as that horizontal line is in between -1 and +1, which is how high and low the sine function actually goes. So what we have to do is restrict this domain so that when I draw a horizontal line, it only crosses the function once. And I know a lot of you would like to restrict your domain between 0 and pi, but even if you restrict between 0 and pi, you draw a horizontal line, anywhere between 0 and pi, it's going to cross that function twice, with the exception of right here. If you were tangent at y equals 1, it would cross once. But so that's not a good number. Okay, we're not going to start at 0. We want the biggest possible domain interval for which the sine function is one-to-one. And that ends up being the biggest possible domain interval for which you have all values between -1 and 1. So it just seems logical to go down here at -1, go up until you hit +1, and consider that right around 0, 0, consider that the restricted domain between -pi/2 and pi/2. Now, people can pick other restricted domains. It's completely fine. Maybe you might want to go from pi/2 down here to 3 pi/2. This would work. The thing is, traditionally, that we like to include really small values in our domain, our restricted domain, so we try to stay right around 0 if we can. So being around 0 would mean that we would have to go from pi over 2, negative pi over 2, I'm sorry, to pi over 2. So this is the restricted domain. If I showed you just y equals sine x from pi over 2, this is pi over 2, negative pi over 2 to positive pi over 2. This is the restricted domain, and sure enough, any horizontal line that I draw is going to cross this function exactly one time. So that makes y equals sine of x 1-to-1 on the domain between negative pi over 2 less than or equal to x less than or equal to pi over 2. All right. Now, does this have a whole lot to do with what I'm about to work on in this video? Probably not, but I would really be a miss and a failure if I didn't talk about this before I moved on. Okay, so the inverse function. In order to find the inverse function, I want to find an expression for the inverse function, which is really kind of simple to do. Basically, we simply take the sine function that's given up above here, this thing, f of x equals sine x, and we simply put an inverse symbol on it. So we write sine inverse of x, which is kind of like saying sine of x is inverse. Okay? But we don't like this notation because it kind of looks like this. Doesn't this look like 1 over sine of x? And we don't like the notation of putting the negative 1 in here a whole lot either, because it looks like I have an exponent of negative 1, when really this is not a negative 1 exponent I'm talking about. It's an inverse symbol. So I'm going to get rid of all of this and tell you that in order to eliminate that inverse symbol, mathematicians have decided to call this function arc sine of x. And sometimes they leave it as f inverse of x, because I don't think people are going to conceive that thing as being anything but an inverse function. But this is what we're going to call the inverse function of x, which is arc sine of x. So if I let this be a y, and I say y equals arc sine of x, basically I'm saying something like y is the angle whose sine value is x, end quote. And for the inverse function, remember, if the original function and the domain were angles and the range for the original function were ratios, the inverse function is going to go backwards. And now I'm going to be applying arc sine not to an angle measurement, because I'm not dealing with the domain of f, I'm dealing with the domain of f inverse, which means I'm going to be playing with a ratio. Arc sine of the ratio is actually equal to the angle. So I know it twists, it goes backwards, but I'm sine of the angle is equal to the ratio. And these are kind of backwards from each other. That's what makes them inverse functions. Okay? So what we want to talk about today is the derivative of the inverse function. So I know that the derivative of sine of x is cosine of x. I want to figure out what is the derivative of arc sine of x. So there's a few different ways to go about doing this, and this is our objective for today. I want to know what is the derivative with respect to x of arc sine of x. And I really don't believe I should be leaving a space right there. I think that's one function, arc sine of x. This is the big question. So I am going to actually make an equation for this thing, and I'm going to say, well, y is the angle whose sine value is x. And I am going to rewrite this just a little bit so it makes a little bit better sense and get that arc out of here, because this is the thing I don't know how to take the derivative of. So I'm going to rewrite this, and I'm going to say that the sine of my angle, which is this y right here, this is my angle, is equal to x. Okay? Let's just see how this works a little bit. Now I'm going to take this y equals sine of x, and I'm going to do an implicit differentiation. So the derivative of sine of y, let me see, I'll just write this out here nice and neat for you. The derivative of sine of y will therefore be the derivative with respect to x of x. Just take the derivative of both sides with respect to x. The derivative of sine of y is cosine of y dy dx, chain rule, because if I were only taking the derivative of sine y with respect to y, then yes, it would be cosine y, be done. But I'm not. I'm taking the derivative of sine y with respect to x, so I got to dig into that angle measurement and use the chain rule. This on the right-hand side, I'm asking what is the derivative with respect to x of x, and that's nothing more than dx, which is just 1. So here I have dy dx is equal to 1 divided by cosine of y. Let's not forget, y is an angle, right? Y is an angle. Y right here, when I set this thing up, y was the angle whose sine was x. Okay? All right, let's keep going here. So this is all nice, but I would like this in terms of x instead of something else. So let's draw a picture with this given information, and I don't really care if you take it from this top piece or the second piece, either one. I want to just draw an angle measurement. I'm going to call that angle y right there, and I'm going to go ahead, and this would be radians, not degrees. I'm sorry about that. Radians. Everything in calculus is radians, so this is y radians right in here. Let's see where I am here. The sine of the y value, which is opposite, this is my opposite leg over here, over hypotenuse. So the sine value is opposite over hypotenuse, and that answer is x over 1, because I don't have anything underneath that x, so it's just x over 1. And I can use the Pythagorean theorem to find out what's missing here. Pythagorean theorem says that leg squared plus leg squared has to equal the hypotenuse squared. One of the legs I don't know, squared, plus the other leg is x squared, equals the hypotenuse, which is a 1 squared. So again, this thing is something I don't know, squared plus x squared equals 1. So I'm going to subtract x squared from both sides of the equation. I'm going to get that my last leg here being squared is 1 minus x squared. And I'm going to square root both sides, and it's going to give me my missing piece is the square root of 1 minus x squared. Now, if you're in my class, you're probably thinking, oh, you forgot to introduce the plus and minus sign when you introduced the square root. At least I hope you're thinking that. And I really should show you that I thought about it and put the plus and minus sign in here. However, what I'm trying to find is the length of a side of a triangle. So the length of the side cannot be negative. It has to be positive. So I can just leave the plus and minus sign off it and just keep going from here. Okay? So that means that this question mark right here is the same thing as the square root of 1 minus x squared. Now here I am over here at angle y. This is my position. And now I want to talk about what is the cosine of that angle measurement. So my dy dx turns into 1 over, and cosine compares the adjacent to the hypotenuse. And so my adjacent is the square root of 1 minus x squared, and my hypotenuse is a 1, which I don't have to write it. It's negligible because it's a 1. So dy dx is equal to 1 over the square root of 1 minus, whoops, I don't like that, the square root of 1 minus x squared. And what was my y? Go back up higher. My y right here, my y was arc sine x. So this means that the derivative with respect to x of y, which is arc sine, I do it all the time, arc sine of x is equal to 1 over the square root of 1 minus x squared. And this is a formula that we have that allows us to take the derivative of the inverse function of x, okay, or arc sine x, the derivative of arc sine x. This is one way of proving the derivative of arc sine x. There's another way to prove the derivative of arc sine x, which I'm sure you're not interested in, but I'm going to throw it down here anyway for the sake of doing it. I could just basically say that the sine of the angle arc sine, the sine of the angle whose sine is x is x. Sine of the angle whose sine is x is x. That's like I'm talking in circles. Okay? And that's true though. The angle whose sine is x. I don't know what that angle is, but if I want to take the sine of it, I'm going to get x. It's just wrapping in circles, and it shouldn't be very complicated. It's actually so simple that it might even be difficult. I don't know. But we're going to go ahead and we're going to differentiate both sides of this equation. So we're going to take the derivative with respect to x of sine of arc sine of x is equal to the derivative with respect to x of just x. And we'll differentiate both sides, and we'll come right back to the same formula. So let's see. The derivative of a sine function is the cosine function. So cosine of, and remember, your angle never changes. So arc sine of x. However, we now have to do the chain rule because we've got to take the derivative of our oogie boogie, so to speak. So I have to multiply by the derivative with respect to x of arc sine of x is equal to 1. Okay, now I have to figure out what this thing is right here. Okay, let me just go ahead. I'll say the derivative with respect to x is equal to, oh, silly Gina, sorry, the derivative with respect to x of arc sine of x is equal to 1 divided by cosine of arc sine x. It's not as hard as it looks. I'll lead you through it nice and carefully here. Yikes. Okay. So I want to find the cosine cosine of the angle whose sine is x. I'm going to write that in words. Find the cosine of the angle whose sine is x. That's what I want. So I'm going to draw a little triangle, and I'm going to go ahead and put my angle right in here. I don't care what the angle is, and I'm going to measure the sine as being opposite over hypotenuse as x over 1. And then I'm going to go through the Pythagorean theorem like I did a moment ago. I'm going to come up with this being the square root of 1 minus x squared. And now I'm going to play with the cosine of this angle. And cosine will be adjacent over hypotenuse. And the square root of 1 minus x squared divided by 1 is the square root of 1 minus x squared. So this comes right back down, and on my denominator I write the square root of 1 minus x squared. And I have a 1 on top, and lo and behold, this is the formula, again, for the derivative with respect to x of arc sine of x. Same formula, same problem, just a different method of getting at it. All right, let's do a couple of examples and see how it's used. And, you know, before I do an example, I think I want to generalize this statement just a little bit, because everything I'm doing right now is with respect to x. And what if I had a little oogie boogie embedded in my angle formula up there? So I think I'm going to generalize this with a u, okay? So I'm going to write these formulas again in one spot so everybody gets to see them. And you know what? I think I'll even change colors and make it a little more noticeable for everybody. Good enough. Okay, so we have this one formula that says the derivative with respect to x of arc sine of x is equal to, big fraction, 1 on the numerator, square root of 1 minus x squared on the denominator. And now we are going to generalize it. And I'm going to say to you that the derivative with respect to x of arc sine of u will equal, same thing, 1 over the square root of 1 minus, this time I'm going to write u squared. However, now you need to chase it with the derivative of u with respect to x. This is your chain rule right here. So a lot of people don't put this piece here. A lot of people would not write this. I'm going to erase it. And instead of writing a 1 on the top, I'm going to write a u prime. Is that okay? Because u prime And it shouldn't look like u to the first, it should look like u prime. I don't know if that made much of a difference or not, but that's what the generic formula looks like. Okay, let's back this up. Let's say, hey, what if I wanted to go backwards and I didn't want to take a derivative, but if I know a formula for a derivative, I automatically know a formula for an integral going backwards. So let's back this up, and let's say if I wanted to integrate 1 over 1 minus x squared under square root sign with respect to x, I should recognize that as being the answer of nothing more than arc sine of x. Done. And what if I didn't have that? What if I had 1 over the square root of 1 minus something else squared, but then the derivative of that was right here, like with a du? Wouldn't that end up being just arc sine of u? And let's not forget plus c's here on the end, our constants of integration. If you're going to integrate, it's possible that you had a constant on the end of your answer so that when you did take the derivative, it disappeared, became 0, so it wasn't noticeable inside your integrand. Okay, so I'm hoping that these 4 formulas are going to be helpful for you. We're going to focus on this and this, because really, if you know the top one, you automatically know the one right before it, and if you know the bottom one, you automatically know the one right before it. Okay, so let's do a few examples. I have a few set up for you, and we will get busy with this. Okay, here is example 1. Let's switch back to my blue. Here is example 1. I'm going to ask you y equals inverse sine of 5x. I want you to recognize that as being the same thing as arc sine of 5x. Y equals arc sine of 5x. So you can rewrite it with an arc sine if you want, but this does not mean 1 over anything, okay? Please don't think of that -1 symbol as being anything other than an inverse symbol. And I don't mean a multiplicative inverse, I mean an inverse trig function. All right, so I am going to write this as arc sine of 5x because I like the arc sine notation a whole lot better than I like that -1 exponent thing. Alrighty, I want dy dx. That's my question. What is dy dx? Question mark. So it should be kind of simple. Take the derivative with respect to x, and that is going to give you a fraction with the big square root. I like to write my denominator first. 1 minus my quantity squared, and my quantity is this angle, so this is my u, 5x, and my du goes on the numerator, which is just 5. So I can end that right there, or chances are if you're doing, and if I were taking an AP test and it was a free response, I would end right there. I wouldn't go any further. However, if it's multiple choice, they're probably going to make it look like this. Square root of 1 minus 25x squared. So either of these 2 answers are good. All I did was square the 5x. Pretty easy to do, huh? Here's example 2. Let's say y is equal to, how about the integral of a 3 over the square root of 1 minus 9x squared with respect to x. So I want you to go backwards. You might need that formula right there. Okay. First, you need to write it so that it's in the correct format. So we're going to rewrite this problem so that it looks like it's the square root of 1 minus something being squared. So that something would be a 3x. And then you look at 3x, and isn't the derivative of 3x right up here, 3? So this is really fitting for my integral of 1 minus u squared with a du on top. Okay, the square root of 1 minus u squared. So this is just going to be arc sine of what? 3x. And we're going to put plus c on there because we're integrating, and we know that we could have any number added on the end of our integration, because if I took the derivative of this whole thing, this would end up going away, wouldn't it? Okay. Anyway, we understand constants of integration. So let's do another example here. Let's go on to an example 3. Let me bring my screen down. Let's start here. Example 3. Let's talk about y equals 5 inverse sine of 6x squared. Again, this is y equals 5 arc sine of 6x squared. And what do you think I want you to do with this? I want you to find dy dx. That's what I'm looking for. Dy dx equals question mark. So we can just like jump right at it if you want, if you're real intuitive. And if you're not real intuitive, that's okay. We can go to the side and we could say let u equal 6x squared. And then you can take your du, and this would be 12x dx. And you can say, I don't have a 12x dx. You know, I'm totally integrating, and I shouldn't be doing that. But that's kind of weird. Okay, so let's just do this the way we would do this if we were differentiating. Okay, so I want the derivative of y with respect to x. But I am going to have to take the derivative of, let me write the u part in there first before I do this. Y equals 5 arc sine of u. So I want the derivative of y with respect to x. I copy the 5 just comes along for the ride. Now I need the derivative of arc sine u. We should know the derivative of arc sine u looks like this, 1 minus u squared. But don't we have to multiply this by the derivative of u with respect to x? This is my chain rule right here. So putting everything back into play, my dy dx becomes 5, and I am looking at square root of 1 minus, what was my u? 6x squared, quantity squared, and my du dx is 12x. So we're going to clean this all up nice and finish our answer. By the way, on an AP test, I would stop right here. That would be good enough. But I'm going to let this indicate what a multiple choice AP question might look like. 5 times 12 is going to give me 60x over the square root of 1 minus, and probably not 6x squared, but probably 36x to the 4th. Would be a multiple choice question. Now let's just do this again a lot faster in a more intuitive manner. Okay, it doesn't really take this long. You don't have to go through setting up a chain rule and everything for all of that. Let's see, let's start it one more time again. I'm going to move over. I'm looking at y equals 5 arc sine of 6x squared. So dy dx is equal to, I'm going to leave the 5 alone. This is the square root of 1 minus something squared, and whatever I put here, its derivative is going to go up on top. So what am I putting down here? Hopefully you know it's just automatically 6x squared, and the derivative of 6x squared is 12x. And I'm done. I can go a little further and simplify if I want to, but this is just going to give me 60x over the square root of 1 minus 36x to the 4th. Look how fast that really is. I want you to understand what the chain rule is doing, but you can pretty much hit that chain rule right in your head and put it right on top. All right, let's do example 4, and I think that is going to wrap us up here. So let's go for example 4. Let me ask you if y is the integral of 3x to the 7th over the square root of 1 minus 25x to the 16th with respect to x. How do I go backwards? I need to make this look like the right thing. The first thing I'm going to do is rewrite this square root thing into 1 minus something quantity squared. Now what is it that gets squared to equal 25x to the 16th? And I'm hoping, I know you get the 5, but I'm hoping you don't say x to the 4th. I'm hoping you understand it's x to the 8th. So this is 5x to the 8th. Okay, so I don't need this here. On the top, I still have 3x to the 7th, and then I have a dx. I think it is nicer right now to go ahead and do a u substitution and get this thing written in terms of u, because the derivative of 5x to the 8th is not 3x to the 7th. Now, We could do it kind of fast if you'd like. Do you know the derivative of 5x to the 8th? I'm hoping you know it's 40x to the 7th. So I really, let's see if you can follow me. I really could take this 3 and pull it to the outside. That would give me 3. I want a 40x to the 7th on my numerator so that the derivative of this 1 minus quantity 5x to the 8th quantity squared, so that the derivative of this 5x to the 8th is sitting on the top. But in order to put a 40 on top, I have to divide out a 40 as well. Does that make sense? That's kind of intuitive. The 3 comes out, and look, this 40 over this 40 is really like the number 1. So I'm changing the appearance of this integral without changing the value. This ends up being dy dx. Sorry, not dy dx. I don't want a derivative. I just want my integral. Y equals, copy the 3 over 40. This I recognize, right? Or I should not circle the integral. This I recognize as being the derivative of arc sine. So arcsin of what? Of 5x to the 8th. Whoops. Battery is running low. I thought I was plugged in. I am plugged in. Yeah. I'm not sure. Okay. So put a little plus c on the end of this, and we are done. We can go through the u sub, which I do think is kind of important to practice this a little bit. Let's do this. Y equals the integral of 3x to the 7th over the square root of 1 minus 25x to the 16th dx. I could go to the side. Of course, I first have to get my y equals again. Don't I have to get this put up in the right format? 1 minus 5x to the 8th quantity squared, and on the top 3x to the 7th dx. And I can go to the side and I can say let u equal 5x to the 8th. Then du is equal to 40x to the 7th dx. Well, I don't have 40x to the 7th. I have 3x to the 7th. And if you don't want that 3 there, that's okay. You don't have to have that 3 there. We could take that 3 and pull that to the outside and say, don't look at me. I don't want to be part of this problem. So I can just call this that integral. And I can say, well, get rid of that 40. I don't want that 40 there. So I get 1 over 40 du is equal to x to the 7th dx. Well, here's x to the 7th dx. This is the same thing as 1 over 40 du. This is my u. I'm ready to write this in terms of u. I get 3 times the integral of 1 over the square root of 1 minus u squared times 1 over 40 du. That 1 over 40 can come to the outside, yielding 3 over 40 times the integral, and I'm taking baby steps with you, I know, 1 minus u squared under here, du. Then you recognize what's here as being arc sine, and then you, or the derivative of arc sine, right? This, the integrand should be a derivative of something. So 3 over 40 arc sine of u plus c, and then we put our u back in, and we get y equals 3 over 40 arc sine of, what was my u? My u was 5x to the 8th plus c, and this answer should be the same exact answer I just had up here. So these are good. Okay, I think we are going to call it quits right here on our arc sine function. So we should be able to take the derivative of arc sine, and we should be able to integrate our 1 divided by 1 minus u squared du and get an arc sine of u plus c. Okay? I hope so. Let's end this thing and say, Talon out. I don't like that. I'm going to do it again. Talon out. Whoop, whoop. Bye, guys.